All right, so like I said, today is all about free energy. So last time we did that heat engine example, and I just want to say that Gibbs free energy, that the second law can do a whole lot more for us chemists than that. And so today we're talking about G, the Gibbs free energy. And I hope it'll answer some questions that you might have had all these years about Gibbs free energy. I'm sure you've been brewing all these Gibbs free energy questions in the back of your mind, like why is it called free energy? Anyway, so Gibbs free energy, I guess I would say, is the chemist's way of looking at the second law. And we associate spontaneity with negative delta G values, whatever that means. Okay. So anyway, and we're going to also talk about extra work. All right, so I'm going to start, as you might imagine, because as I said, the Gibbs free energy is the way that chemists think about the second law. So I'm going to start with the second law, which is different ways of writing it. You know, delta S total, that's the sum of the system entropy and the entropy change of the surroundings. So entropy change, I mean, to the system, and the change of the surroundings is greater than 0 for a spontaneous process and is equal to 0 for a reversible process or an equilibrium process. Now we're going to actually use the differential form. And so we'll start with ds plus ds surroundings is greater than or equal to 0. And that thing that I write there is true all the time, right? There's no restrictions placed on this. This is generally, actually, I'm going to say true in general. That's even more clear. So what we're going to do is work with this expression and try to take the surroundings out of this situation. So we're going to figure out what restrictions we can make, things like that, to get rid of this. We want to get rid of the surroundings. And the book has a great section in the chapter. It's called Focusing on the System. Okay, so that's really what we're going to be doing with this derivation, at least part of it. So what we do is we start with the most general form of the second law, and that's what I have written down here. I say it's true in general. And then one step at a time, we move on by making conditions, by setting conditions to an expression that involves only system parameters. Okay, so we add conditions until we have an expression that only depends on system parameters. All right. Okay. So we start, like I said, with that ds plus ds sur is greater than or equal to 0. And now let's see. First thing we're going to do is we're going to use the definition of delta S surroundings, or ds, I should say. And that definition is that ds surroundings is dq surroundings over t surroundings. Okay, so So it seems like we're failing, right? Because now we have surroundings in two places, but no, we're going to get rid of it. All right, so now this is still general. I haven't done anything that makes it not general. And now I'm going to also say that dq sur equals negative of dq. And that is also completely general. This is also completely general. It's always true. All right. So I'm going to go ds minus dq over t surroundings is greater than or equal to 0. So it's still general. Okay, so in fact, this thing, believe it or not, this crazy inequality actually has a name. It's like so important that we give it a name. It's called the Clausius Inequality. Anyway, so that's kind of like the last step before now we have to start throwing conditions into the mix that will make this relationship less and less general. So I think they give the most general that you can get with that from the second law. They call it the Clausius inequality. But anyway, okay, so now we're going to throw in conditions. Okay, so the first thing I'm going to do is say that the system and the surroundings are in thermal equilibrium. So what can I do when I do that? What does that mean, thermal equilibrium?
They're the same temperature.
That's right, T equals T sur. The second thing I'm going to do is I'm going to say constant pressure. What just happened there? What the heck happened there? This damn thing shifted all my notes around. Ah, I don't believe this.
Try your undo.
Oh, well, too late for that. I'm all excited, about this. I like this class. This is what we do today. But of course, my computer doesn't care. All right, so constant pressure. So it's like a bench top, right? So what that does to this is I'm going to be able to, oh man. Okay, so ds minus dq over t is greater than or equal to 0. Okay, replace t surroundings with t. And now I'm just going to call this dqp, right? Because I said constant temperature. All right, so now I have this. All right, so now we're getting there, right? Because this dqp, what's that? What's the heat that flows at constant pressure?
It follows.
It's just dH, right? Remember that? It wasn't that long ago. Remember delta H is QP, DH is DQP. All right, anyway, well, here I am telling you that that's what we're going to do. And now I'm going to tell you that's not really quite right. But if that were true, we would have this. Okay, but there is a hidden condition in this relationship. And so now, since you didn't remember this, I'm going to rederive it, and we're going to figure out what is the hidden condition. Okay, So let's go back to that derivation. Okay, this was when we derived dH is dQp. Let's do it again. Okay, so we start with, so we already we're already off on quite the tangent here. That derivation started with the definition of the enthalpy. Then we took the differential, which is like the derivative of both sides. Okay, then we used the product rule on this term, plus PdV plus VdP. Okay, now we use the first law, but this is really where we made a restriction, because there are actually two kinds of work: expansion work and extra work. And we still have this. And what we said back then was that there is no extra work. And so we got rid of that term. Okay, so that meant that we just had here dq plus dw expansion plus pdv plus vdp. Well, I don't know why I'm carrying this vdp, because I already said that the pressure is constant somewhere. See, so I really should have gotten rid of that, because this is 0, because dp is 0. This isn't even here anymore. So we have this now, dH is dq. Ah, look at this. So, hold on a minute. Something is, oh yeah, we have to put in dW expansion is minus P external dV plus P dV. So I use the definition of expansion work. Okay. And now I'm going to have another condition. So, you know what? It was confusing two derivations. dP is 0. I have to say constant pressure. This is not the same derivation as the one where I had said constant pressure. Dummy. Oh, whatever. So constant pressure gets rid of dP. All right. Anyway, I don't know. So now I'm going to say that the system and the surroundings are in mechanical equilibrium. So what can I do when I do that? What does that mean, right? That means that the pressure of the system is the same as the external pressure. And that's great, because then I get to cancel these two terms. And I get, hold on, I forgot the dW expansion. I mean, oh no, that's right, I'm sorry. I'm a little lunatic here. Yeah. Right, I already said no extra work. Okay, so that means dH equals dQ, and the P means at constant pressure. Okay, so that was the derivation of dH is dQp. But what if I go back a couple of steps and I didn't say there was no extra work? If there is extra work, then dH will be dQp plus dWe, because we wouldn't have canceled it out here. We'd still have it. Are you guys okay with that? Okay. Oops. Okay. So if there is extra work, we actually have this relationship. So if there is extra work, we have that. And if there's no extra work, we have this one. All right, so now we're done with the aside. The aside is done, right? This from there to there. That's the aside. So what is the hidden condition? Now we can answer it. No extra work. So I can write this ds is dh, sorry, not equal to, minus dh over t greater than or equal to 0. So what are the conditions? Okay. First of all, we had the system and the surroundings in thermal equilibrium. All right. Then we had constant pressure. Then we have to use all the conditions that were set in this derivation. And in this derivation, we had mechanical equilibrium between the system and the surroundings. And we had no extra work. So we have to add that to the list of conditions here. So this is really in order for dq p equals dh to be true. We had the condition that P has to equal P external, and also that DWE equals 0, no extra work. And so we end up with this relationship, which very easily could become TDS minus DH is greater than or equal to 0. But what I'm going to do next is I'm just going to multiply by -1 to get DH minus TDS is less than or equal to 0, right? I have to change the sense of the inequality. And now I'm going to tell you the definition of the Gibbs free energy, which is the enthalpy minus the temperature times the entropy. So that means that DG would be DH minus, now I have to use the product rule. And I'm almost looking at this, right? But what condition can I make to get rid of this term here?
Isn't that from the thermal equilibrium?
No, this is the definition of the Gibbs free energy. But what can I say to get rid of a DT? When is there no change in temperature?
Temperature.
When temperature is constant. So if the temperature is constant, I can get rid of this term. So now I have that DG is DH minus TDS. And all I have to do is add a fifth condition that the temperature is constant. And from above, from this thing over here, I know that this is less than or equal to 0. So this is true. DG or DH minus TDS is less than or equal to 0. This is the same thing. When all these conditions, we have system and surroundings in thermal equilibrium, constant pressure, P equals P external, no extra work, and constant temperature. That's a lot of fine print, but what it does say is that the change, that's nice. I can see it's going to be a great day. This thing is going nuts. So we have dg is less than or equal to 0 with all of these conditions, which means delta G is less than or equal to 0 in integrated form.
Doctor, can't see.
Oh God, this thing is. Now it's got two of those open. Why are there two of them open? It's got two identical things open. What happens if I close the other one? All right, that's what I'm doing. All right, so the change in the Gibbs free energy must be less than or equal to 0 for a spontaneous process and equal to 0.
I still can't see that. I'm sorry.
Why? Okay, I'm back now. Very confusing what's doing today. Maybe it's the weather. Anyway, this is the result. It comes from, well, you saw what it came from. And there's really plenty of fine print. Right, all these conditions here. I know you got some copying down to do. So, you know, you look at this and you say, oh man, look at all those conditions, right? All those things. But you have to remember something, okay? You have to remember that, so Gibbs free energy is made up of, you know, it's an enthalpy plus TS. Since temperature, entropy, and enthalpy are all state functions, that means G is a state function. So that means if we're really caring about like the difference in Gibbs free energy, you know, before and after a reaction or something, or changes during a reaction for part of a reaction, we don't have to have thermal equilibrium the whole time. We don't have to have constant pressure the whole time. We don't have to have these conditions the whole time. We don't have constant temperature the whole time. The reaction can happen, the temperature can change, and then it goes back to this temperature of the room. All that has to be true is that the temperature has to be the same at the beginning and the end. Pressure has to be the same at the beginning and the end. All these conditions have to be true at the beginning and the end. So they're not as restrictive as you might think. Just want to say that because it looks like, you know, when are all these conditions going to be true? Well, we use Gibbs free energy in all kinds of places. We say, let's assume this reaction happens at 298 and it's got a delta H of negative 300 kilojoules. Now, you know, the temperature is going to change, but that's okay because after all that heat flows out into the surroundings, system comes back to 298. And we know what the deltas were, because it doesn't have to be constant the whole time. Doesn't matter how the system got from point A to point B, it just matters that it did. So anyway, so that it's not as restrictive as you might think. Okay, so let's see, we have some, so we have this delta G is less than or equal to 0. So we have, first of all, we had dG is dH minus TdS. Now, if I said that the temperature is constant, right, then I could integrate this and I would be able to leave the temperature out of the integral. So this would mean that delta G is delta H minus T delta S. So you should keep in mind that this relationship that we use all the time is valid at constant temperature, okay? So what I want to do is think about the signs of the delta H and the delta S. All right, so there's really 4 different possibilities of what these signs can be, right? You could have delta H positive, delta S positive, positive negative, negative positive, and negative negative. There's really only 4 different things that can happen. And so what I'd like to do, we're going to go through, actually, we're going to do 2 of these we're going to do in class, and 2 I'm going to ask you to do at home. But what I want to say from the outset is, what does delta H have to do with? What delta H has mostly to do, well, you know what it has to do with, because it was actually something that we did on that quiz, right? Delta H has to do with the energy needed to break bonds and the energy released on making bonds in a chemical reaction. Right? So all the bonds that are broken, those are all positive delta H's. All the ones that are released, those are negative delta H's. Add them all up, and that's what delta H has to do with. What does delta S have to do with? Well, delta S, as we've seen, when you make more moles of gas, and so that is better able to disperse energy, or you go from something complicated to more things that are very simple. So delta S has to do with the increase or the decrease in the order of a system, which has to do with its ability to disperse heat. Okay, so delta H and delta S are unrelated. If they were related, you wouldn't see all 4 of these, right? They would, there'd be some kind of correlation, but there actually isn't. Okay. However, delta H is related to delta S surroundings. Okay, so if I take a little box and I draw this as my system, and suppose I have an exothermic reaction. So heat is transferred into the surroundings, all right? So an exothermic reaction has a delta H that's negative, and that leads to a delta S surroundings that's positive. In fact, delta S surroundings is directly related to delta H. Delta S surroundings, okay, it's Q sir over T sir, right? So that's equal to negative Q, which at constant pressure is negative QP over, and if we say that the system and the surroundings have the same temperature, then this is the negative of delta H over T. Don't you see that? Because heat is leaving the system, delta S sir will be positive when delta H is negative. All right. So so delta H is very closely related to delta S surroundings, but it's not related to delta S. And the opposite, of course, is true as well. If the reaction is endothermic and heat is going into the system, Q is positive, QP is positive. Let's say there's no extra work, so we can say that's delta H. So Q sir over T, again, negative delta H over T. So delta H here is positive. So delta S surroundings is negative. Here we had delta H negative, delta S surroundings is positive. But not only are they opposite signs, there's a very specific relationship between delta H and T that gets you to delta S surroundings. And there's the same, relationship whether regardless of whether the reaction is exothermic or endothermic. Okay. So so I'm going to go to the next page where I have a handout. And there's 4 different situations that are outlined in this handout. So the first one, it says if delta H is positive and delta S is negative, we can analyze the signs of the 2 terms in the delta G. Okay, so if delta H is positive and delta S is negative, then of course the delta H term is positive, but the negative T delta S term becomes positive when you multiply by minus T. So this question says, can you tell for sure if the reaction will be spontaneous? And I should clarify that we're talking about under standard conditions, because that's what these little zeros here mean. I'll talk more about that later. But anyway, so what we have here is that this is an endothermic reaction, right? Because we have positive delta H. Heat is required. And we also know that there is more order or less disorder on the product side because the delta S is negative. So when this situation happens, well, both of these terms are positive. So what it says is, can you tell for sure if the reaction will be spontaneous? And I'm saying, yes, you can. This reaction will be spontaneous under standard conditions at any temperature. Because look at the role of T in here, okay? T is something that's always positive, right? T can't be negative because we're talking about Kelvin units, right? T can't be negative. So minus T delta S is always positive when delta S is negative. So no amount of changing the temperature is going to make the sign of that delta G be negative. Okay, so I guess I would say that, God, I said spontaneous and nobody stopped me. Non-spontaneous. It will never be spontaneous because, of course, we know delta G has to be negative. Sorry about that. This reaction will not be spontaneous. At any temperature, because those terms will always be positive. All right, so I'm going to leave you to do this one. And I'm going to go over to 3 here. So this is number 3. Delta H is positive and delta S is positive. Well, that means that minus T delta S is negative. So now we have 2 competing terms. We have an endothermic reaction. All right, we have a positive delta H. But now we have that entropy increases. So that leads to a negative minus T delta S term. And so that means that we don't know what the sign of delta G will be. So the answer, can you tell for sure, is no. Can't tell if delta G0 will be positive or negative. So now we have to think of, would temperature affect this conclusion, right? So the answer is yes, right? Because the negative T delta S term, the magnitude of this term will increase as the temperature goes up. So at a low temperature, at a low temperature, it will have a, if you can pick whatever low temperature you need, it will have a magnitude that is smaller than delta H. At low temperatures, this T delta S will be smaller than delta H because it depends on the size of T. Okay, and when that happens, okay, that means that delta G will be negative. Wait a minute. No, it'll be positive. I knew it was wrong. So that's because this negative term here will not be so important at low temperatures. So at high temperatures, this T delta S term will become larger, right? Because delta H and delta S really aren't changing much with temperature, but temperature is changing a lot with temperature. Okay, so at this point, delta G0 will be negative. So that means we have kind of a, if I put temperature here, that there's a temperature which I tend to call the crossover temperature. This happens when both delta H and delta S have the same sign, because when you put that minus T delta S, it means that those terms have different signs. So that means there will be a temperature where this reaction will go from being non-spontaneous to being spontaneous. Okay, what is that temperature? Well, it all depends on the relative magnitudes of these two terms. So, so it's when they're equal, right? When delta H equals minus T delta S, well, minus T delta S and T delta S, the same thing, because it's the absolute value. So the temperature will be delta H over delta S. Okay, so if you take and divide the delta H0 by the delta S0 and you get a temperature, that's the crossover temperature. Now, this case, we have delta H and delta S are both positive. So a positive delta S means that at high temperatures, this reaction is going to become spontaneous because that T is multiplied by the delta S. So that delta S being positive will be more important at the higher temperatures. So that's why it goes from non-spontaneous to spontaneous. And this is delta H over delta S. They're both positive in this case, yeah. So then we have the situation where they're both negative, and that means that the entropy change is negative, and so it's when the temperature is lower that reaction will become spontaneous. But I want you to do that one at home, so I'm going to ask you to do that. I think this is a relatively easy problem, so I'll let you do it. How about I'll let you do it for a special problem, but I'll use it to replace a missing one. And I think that this computer isn't working anymore. Let's see. Do you have that big splotch in the middle of your screen? Oh, there it is. All right. So I guess if you've done them all, I'll replace a lower grade. How about, all right. All right. So anyway, just try to get that to me by, it should be able to do it by when. When is that other thing due? Assignment 4. Is that due today? A special problem assignment 4? Okay, so this will be
There's nothing, there's nowhere to hand it in.
Oh, really? Are you sure? All right, I'll have to do that later. All right. Dang it. All right. Anyway, so I think that's pretty straightforward. But there's another insight that I want to tell you about that I talked about on the very first day of class, believe it or not. And that is when you have this equation, which is of course only true at constant temperature. And if you multiply both sides of this equation by -1 over the temperature, you get negative delta G over T equals negative delta H over T plus T delta S over T. All right. Now, these T's cancel here, obviously. And this is minus Q over T, which is equal to Q surroundings over T. Everything else stays the same. And what is Q surroundings over T? Suppose the temperature, we're in thermal equilibrium, this is T surroundings. This is delta S surroundings. So what can you conclude from this?
The negative delta G over T equals the total delta S.
Yeah. So now you could see why having a positive delta S total means having a negative delta G, right? Because they're very closely related to each other and they're opposite signs. So this free energy is closely related to total entropy. All right, so let's look a little aside. All right, so there's more to be done on this Gibbs free energy. And so first of all, why do we call it the Gibbs free energy? And the answer to that is that it's actually a measure of the energy a system has available to it to do extra work, okay? Finally, we're here with extra work. So that's what it is. The Gibbs free energy is a measure of the amount of extra work that a system can do. So what types of extra work? Well, there's electrical work, like with chemical cells, fuel cells, things like that. There's chemical work. Now, what do I mean by chemical work? Well, that's where, say, one reaction with a negative delta G helps to drive another reaction with a positive delta G, because when they're coupled, they have a negative overall. So anyway, so electrical work, like I said, well, I didn't say it yet, but this is how reactions with negative delta Gs can be used to generate electricity. And this is like how a reaction with a negative delta G0 can be coupled to a reaction with a positive delta G0, so that overall the delta G0 is negative and it becomes spontaneous. Okay, so this is very used in biochemistry, where the ATP hydrolysis, for example, which has a negative delta G0, is coupled to all sorts of reactions. That's extra work. All right, so that's the most common example. So I have to show you where this comes from. And I'm going to do that with this little derivation here, which normally when I teach this in the classroom, I have students, I just let you do it. So I think I'm going to give you a few minutes to try to do this. So basically what it is I tell you what to do, write the differential form of G, the differential of G, sorry, given the fact that G is equal to H minus TS. So in other words, dG is, so we'll take D H minus TS and go with that and do term by term. You have to use the product rule for the TS. And then I tell you to use the definition of H, use the product rule again. And then it sort of takes you down this derivation. So I'm just going to give you a few minutes to work on this, like maybe, like 5 minutes or something like that. Just so you could see, think about it for just a few minutes. Try it out, okay? How far did you get?
Step.
I think I'm gonna go through it now. All right. So see how far you got.
Do you end up with no TDS? Like at some point, do you cancel out TDS? Like
No, what?
at some point, like at the end, do you have no TDS? Like, right?
Yeah.
Okay. So I think I'm on. I think I'm on the right step, but I'm still trying to do it.
Okay. So I use the product rule for the TS. Now I'm going to use a definition of H. Then the product rule for the PV. Then I'll say constant pressure. So I will cross out this one. And constant temperature. So I have dG is du plus PdV minus TdS. I forgot something, didn't I? Oh, no. Okay, now I have to use, I don't remember what order, but now use the first law. Okay, I am in the right place. dQ plus dW expansion plus dW extra plus PdV minus TdS. Okay. Now I'm not going to get rid of that extra work because that's what this thing is all about here. But I'm going to put in the definition of expansion work. I said I was going to, and I didn't. Okay. Now let's have mechanical equilibrium here. P equals P external. So that allows me to get rid of these two terms. So now I have dG is okay. So now let's put in the definition of ds. So now these t's cancel. And we have dq plus dwe minus dq reversible. So if we now say that we're dealing with a reversible process, this is a very real constraint. All right. So if the process, if this reaction or whatever it is reversible, then I get to cancel these two. And I end up with dG equals dWe, or delta G is equal to the extra work. Okay. Did you get almost down there at the bottom? Made it pretty far? Good. Okay. So this is a pretty important result. So it says that for a reversible process, with all these other constant temperature, constant pressure, P equals P external, mechanical equilibrium, that the delta G is equal to the amount of work that system can do. But in fact, I'm not going to prove it. But what's really the case is delta G is equal to the maximum amount of work, of extra work a system can do. And that maximum, guess what? And that maximum is for a reversible process. No surprise there. We've seen that before, right? The maximum work the engine could do is also for a reversible engine. So, anyway, we did say it was reversible, but what we didn't prove was that led to this WE being a maximum, but it is the maximum, and we are going to use that. So what I'm going to do is continue with this. I'm going to actually do an example. I'm going to show you a redox reaction, very simple redox reaction. And I'm going to talk about running this reaction in two different ways. In the first way, it's going to be nice and slow and controlled, and you'll see how. And the second way, it's just, put everything together, let it go. Let it do what it's going to do. Let it go spontaneously. So the first way is going to be what I say is a reversible way, and a second way is a spontaneous way. Okay. So maybe this seems a little theoretical until we actually do it. So when this is done in the reversible way, we get the maximum extra work. Spontaneous, let it go, no extra work. And so I'm going to go through that example with you, and I think it'll make this much clearer than just, just saying it. An example is worth a lot. So let me go ahead and do that example. So I hope that some of you have printed this out, because it's going to go by awfully fast. That's why I sent that email earlier. Okay. So this is a setup, and this is for running the reaction reversibly, right? This is for the reversible way. So I'm just going to show you the setup here. I have a zinc electrode on one side, a silver electrode on the other. Here's a solution of silver nitrate. So that means I have silver ions and nitrate ions, but we don't really care about the nitrate ions. And here I have a zinc electrode in zinc nitrate. So the zinc ions are what I care about here. And so the first thing I'd like to talk about is which way are the electrons going to flow? Because notice there's a wire here connecting these electrodes, okay? And so if the electrons flowed from right to left, in this direction, what would that mean? Okay, that would mean that the silver is giving up an electron, that the silver is getting oxidized to silver ion. And those electrons would flow through the wire down to the other side, and the zinc ions would pick up those electrons and form zinc. And if that happens, then the reaction would be 2 silver metal, 2 silvers plus zinc ions gives you 2 silver ions plus zinc metal. Okay, that's one possibility. Now the other possibility is that the flow will be in the other direction, okay? And in that case, the zinc would be giving up an electron. Zinc would get oxidized, see? Those electrons would flow through this wire to the other side, where they would be picked up by the silver ions, which would be reduced. Okay, so we have 2 silvers. Well, let me start with the metal. It's just the way I've written it here. Zinc plus 2 silver ions goes to zinc 2 plus 2 silver metal. Okay. All right, so these are two ways that this could happen. Which way happens? Only one of these is actually going to happen. So which metal is more active? Which way will the electrons flow? Do you know?
Isn't the zinc more active?
Yeah, from left to right.
So zinc is more active. So we have two reactions here. By the way, these two are the opposite, right? One is the reverses of each other. Zinc is more active. So that means that zinc is more easily oxidized. Zinc doesn't mind being oxidized as much as silver does. So that means that reaction 2 will happen. And zinc will become oxidized and the silver ions will get reduced. Okay, so what will happen is this case here. So that's how we're setting up the quote unquote reversible process. All right. If this were to happen reversibly, obviously it's going to happen a lot more slowly and controlled than if you just threw the zinc and silver ion. So, right, so this is controlled. If you just put the zinc 2 plus and the Ag solid, you wouldn't get any work out of it, right? It would just react spontaneously and you wouldn't get any work out of it. I mean, you don't even have a wire there for electrons to flow through. So that's what I mean by running this in two different ways. Just throw it together. Versus using an electrochemical cell, like the one I showed you up here, okay? So this would be the spontaneous way, and this would be the reversible way, okay? So let's go to the next part. So you can prove this. This is that reaction 2 actually occurs. How can you prove that, right? You can prove it by finding the delta G zero for the reaction, right? If it's negative, then that's the one that's going to be spontaneous, at least under standard conditions. And I feel I should mention that we are talking about standard conditions here whenever we have a little thing on the G. And standard conditions for gas phase reactions is everything is 1 bar pressure. But when you have solutions, it would be 1 molar solutions. That would be the standard concentration. So, all right, so let's find the delta G zero for this reaction. So I've repeated the reaction here. And the way you find a delta G zero is a lot like the way you find a delta H zero, right? It's the sum of the delta G F zeros of the products minus the sum of the delta G F zeros of the reactants. And don't forget the stoichiometric coefficients have to be multiplied by each of those delta G F zeros, just like with delta H's. So here, the delta G zero is, okay, so you'll notice that I didn't give you delta GF zero of zinc solid because it's 0. So we have the same definition, right? If you're forming something from a stable element from a stable element, then delta HF is the delta H is 0 and the delta G is 0. So the delta GF 0 for these, elements in their stable forms is 0. So these are both 0. That's why they're not included. So this is going to be delta GF 0 of the zinc minus 2 delta GF 0 of the silver ion. So using the numbers that I've given you up here, so this would be negative 147.06 minus 2 times 77.11. Okay, so that comes out to negative 301.28 kilojoules. I say kilojoules per mole. I don't really know. I don't care. I don't think it really has to be there now that I think about it. So what that means is that the delta G0 for that second reaction is negative. So that reaction 2 is spontaneous. And that would mean that reaction 1, which is the reverse reaction, has a positive delta G0 and is non-spontaneous. Okay. I think I'm going to stop here.